Hello, good morning. I am SEEMA GARG, Associate Professor in Chemistry, SPC Government College, Ajmer. Today, video 87, lecture 25 is for BSc Part 1, Organic Chemistry, Paper 2, Alkynes, Unit 2. Today, we will see the chemical reactivity of alkynes. Alkynes are less reactive compared to alkenes. Even it has more number of pi electrons. Normally, it gives electrophilic addition reactions. Addition of halogen. In alkynes, because it contains two pi bond and one sigma bond, so it will add 2 times halogens. So first addition of halogen, it will give dichloro, means dihaloalkenes, and on further halogenation it will give tetrahalide product. Alkynes are less reactive in comparison to alkenes due to following 2 reasons. Due to the greater electronegativity of sp hybridized carbon atoms of a triple bond, then sp2 hybridized carbon atoms of a double bond of alkenes. So pi electrons of alkynes are more tightly held by the carbon atoms than pi electrons of alkenes, and hence not easily available pi electrons of alkynes for reactions. One more reason is due to cylindrical nature of pi electrons clouds of alkynes. The pi electrons of a triple bond are more delocalized than that of pi electrons of a double bond. Therefore, pi electrons of a triple bond are less readily available for reaction. मैं थोड़ा सा इसको हिंदी में भी समझाना चाहूंगी. कहने का मतलब यह है कि अल्काइंस के पास 2 पाई बॉन्ड है और एक सिग्मा बॉन्ड है. फिर भी ये अल्केन्स की तुलना में कम क्रियाशील है, क्योंकि अल्काइंस में एक तो sp हाइब्रिडाइज होता है, अल्काइंस जो है sp हाइब्रिडाइज है, और जबकि मोर इलेक्ट्रोनेगेटिव होने के कारण इलेक्ट्रोनेगेटिविटी ज़्यादा है, तो ये जो पाई इलेक्ट्रॉन्स हैं अल्काइंस के, वो कार्बन के साथ बहुत मजबूती से जुड़े हुए होते हैं. मतलब कि कहने का मतलब है कि आसानी से इलेक्ट्रोफाइल के लिए उपलब्ध नहीं होते हैं. दूसरा कारण है कि जो अल्काइंस में जो पाई इलेक्ट्रॉन्स क्लाउड है, वो 2 कार्बन के बीच में सिलेंड्रिकल, मतलब कि एक मूवमेंट करते रहते हैं सिलेंड्रिकल वे में. तो ये जो है, इसकी जो बॉन्ड लेंथ है इसी कारण से कम हो जाती है, और जो है ये पाई इलेक्ट्रॉन्स जो है आसानी से उपलब्ध नहीं होते हैं. Let's see the example. Acetylene means ethyne. Chlorination in presence of carbon tetrachloride, it will give trans 1,2-dichloroethene. On further chlorination in presence of carbon tetrachloride, it will give 1,1,2,2-tetrachloroethane. Mechanism. See here. First chlorine will add, it will polarized, and then negative part means nucleophile part of chlorine, it will add and it will give us trans 1,2-dichloroethene. This trans 1,2 dichloroethene on further chlorination, it will give 1,1,2,2 tetrachloroethane. Addition of HCl. First H ion is added to this ethine and it will give this intermediate. And then on fast addition of nucleophile chloride and it will give this vinyl chloride. And on further addition of H ion, it will give secondary carbon, it may give secondary or primary carbonium ion. There are two possibilities of addition of H ion. But we know that secondary carbonium ion is more stable compared to primary carbonium ion. And this to secondary carbonium ion, this chloride means nucleophile part is further added to the molecule and it will give JM dihalide. Addition of HBr. Unsymmetrical alkynes, for example propine, we can add two molecules of HBr according to Markovnikov rule. But in presence of peroxide, it will work as an anti-Markovnikov rule and it will give JM dibromopropane. So here also addition is according to HBr addition is according to Markovnikov rule and in presence of peroxide it will be anti-Markovnikov. It is very important. Next reaction, metal ammonia reduction reaction. The reduction of alkynes with lithium or sodium metal in liquid ammonia produces trans alkenes rather than cis alkenes, involving anti-addition of hydrogen atoms to the carbon-carbon triple bond. See here, we will get trans alkenes mechanism. In step 1, sodium will give electrons to the alkyne and it will form this anion. And then ammonia will protonate this molecule and it will form vinylic radical. And this vinylic radical will be in two form, that is trans and cis. Trans, as we know, it is a more stable, cis is less stable. And this trans vinylic radical is more stable and on further this sodium will give electron to it and it will form anion and then ammonia will give proton and it will give us trans alkenes. Hydroboration oxidation. As we earlier also seen this reaction in alkenes, here also this boron is a hydroboration reaction and it will form this molecule, right? This enol is rearranged to aldehyde. So on oxidation, then it will be give us aldehyde. Mercuration and demercuration. This is again the reaction which we had seen in the alkenes. Here mercuration and then after that it will form ketone. Dimerization reaction, linear polymerization reaction. Two molecules of acetylene when it is reacted in presence of copper chloride and ammonium chloride, it will form vinyl acetylene dimer. And this vinyl acetylene dimer is on further reacted with acetylene molecule. It will give divinyl acetylene dimer. Vinyl acetylene is used as a starting material for the manufacture of synthetic rubber neoprene. See how vinyl acetylene dimer, when HCl is added, it will give, it will add according to 1,4 addition and in presence of copper chloride, ammonium hydroxide. And this on rearrangement, it will give us chloroprene. And this chloroprene is on polymerization. It will give a synthetic rubber neoprene. So it is very useful product. Second, cyclic polymerization. Trimerization, when acetylene is passed through red hot iron tube, polymerization is occur with the formation of benzene. See here, 3 molecules of acetylene or 3 molecules of acetylene in presence of means it will be when reacted at 600 degree centigrade temperature in red hot iron tube and 15 atmospheric pressure, it will give us benzene. Similarly, trimerization of propyne results 1,3,5 trimethylbenzene, mesitylene. Similarly, like acetylene, propyne also react and it is very useful product. Mesitylene is a very good solvent. It is used for many purpose. 4 molecules of acetylene when polymerized in presence of nickel cyanide at high pressure, it will give cyclooctatetraene. Rearrangement of alkynes, when one alkyne is reacted, means treated with alcoholic KOH, it will give alene and it will rearrange to give 2 alkynes. So it is a rearrangement or isomerization reaction. Reduction. This alkyne we can reduce in presence of platinum carbon catalyst and it will convert it into alkenes and on further reduction it will give alkane. Oxidation. The reaction of alkynes with ozone or KMNO4 leads to the oxidative cleavage of carbon-carbon triple bond with the formation of carboxylic acids. See here, it will give carboxylic acid. When it will be oxidized in presence of dilute KMNO4, it will give ketone. Ozonolysis. In presence of ozone, it will give triozonide and on hydrolysis, it will give ketone and on oxidation in presence of hydrogen peroxide zinc, it will cleave into acids. Nucleophilic addition reaction. Even the concentration of electron on alkyne is more than alkene, but the reactivity towards electrophilic addition is low. But nucleophilic addition reaction could occur in alkynes compared to alkenes. Reactivity will be increased when the electron withdrawing group attached to it. So here, one very unique reaction alkyne can give, nucleophilic addition reaction. So here see, when alkenes are reacted with nucleophile, it will convert it into sp3 hybridized carbon, which is less stable. Anion is sp3, which is less stable. Whereas when alkyne is reacted with nucleophile, it will give sp2 hybridized anion carbon, which is more stable. So alkyne undergo nucleophilic addition because of formation of stable vinylic carbon anion. So due to this reason, nucleophilic addition reaction would occur in the alkynes. Mechanism, see here. Alkynes, nucleophilic addition, vinylic anion, stable vinylic anion is obtained. And then protonation, it will give this reaction. This alkyne when it is reacted, means nucleophilic addition is done in presence of barium cyanide, it will give us this product. So thank you very much for today's lecture.